putting on excitons on lattice. So I haven't been able to put non-equilibrium into my talk yet. Hopefully next time. So this project has been carried on by three amazing members of my group, postdoc Ligo Ma and the two graduate students, Son and Radaf. And the last part is former postdoc, Ji Gu, in the joint group of Kifa Mak and myself. We benefited tremendously by continuous discussion with Alan McDonough's group and his former student, Jie Shan Deng. HBM crystals are from the NIMS Japanese group. So, what is an excitonic insulator? So, excitonic insulator is a charged insulating state that arises from the spontaneous formation of bound electron hole pairs. We call it exciton. This is relatively old. I'm talking about 60s or 70s. Solid state platform for many boson physics. And as you can see from the reference, this problem has been studied by many giants in theoretical physics. So you can think about this from the semiconducting limit. So in this case, if you keep shrinking the band gap of the semiconductor, at some point when the gap size becomes smaller than the exciton binding energy, excitons can form spontaneously. And in the equilibrium, the population of exciton is determined by balancing the energy of negative formation of exciton and the average repulsion energy between the excitons. And this you can think of as like a BEC limit. And this can also happen from the other side, small overlap of semi-metals. And this you can think of as the BCS limit. So there have been some experimental realizations of excitonic insulator. One example is this T-phase titanium selenide from Urbana, in which they saw spectroscopic signature of excitonic insulator. But fundamentally, there are some serious challenges to establish excitonic insulator, especially in three-dimensional bulk materials. And the reason is because electron hole in those materials are often separated in K-space. So you can get insulating states also due to formation of charge density waves. So it's hard to prove that the insulating states arises from the formation of bound state of electron hole. And the condensation does not imply superfluidity, that means zero viscosity. And the excitonic population cannot be easily controlled because that's determined by the band parameters, material parameters. And of course, you cannot control exciton transport electrically. So the idea moving forward is, of course, separating electron hole in two separate layers. And I'm showing one layer, semiconductor or some other, with electron, and another layer with hole. But in between, there is no electronic coupling. They are coupled only by Coulomb interaction. And in that case, you can connect them to electrodes. Then you can continuously tune the density of exciton, which is also chemical potential of exciton. So once you have that, you can do thermodynamic measurements. Then the results will not be complicated by formation of charge density wave or lattice instability. And you can easily dope the construct an excitonic insulator by electrostatic means. And you can control the transport electrically. And because now you have interlayer exciton dipoles, right? And can achieve very strong correlation. As fact, you can achieve interaction much bigger than the degeneracy temperature. So this prevents forming droplets and other states. And the superfluid is expected as long as your sample is clean enough, of course. Okay. And this problem has also been explored by different approaches. This is my only optical pump example. So, you can either do it in coupled quantum wells, applying DC electrical field to tune the well, optically excite exciton, and then they, dissociate and one charge go to the other layer. The problem with this is that the exciton lifetime typically is relatively short. It's hard to reach full equilibrium, so it's not easy to study the ground state property of the system. Or you can look at coupled quantum well, putting them into half-filled lambda levels. So you can think of one layer as an electron and the other half-filled lambda level as hole. And in this case, you need to apply relatively large magnetic fields. And in both cases, the exciton binding energy is relatively weak, either due to dielectric screening or, in case of graphene, and also the binding energy is weak, so degeneracy temperature is only about 1 Kelvin. So we would like to replace them by monolayer of semiconductors. If you can find a pair of semiconductors that form type 2 band alignment, like what I'm showing here, then if you can apply bias voltage between those two layers, and what this bias voltage does is to split this chemical potential Fermi level for electron and hole into two. And this separation can be continuously tuned by that bias voltage. So now if I increase my bias voltage, and at some point the effective band gap, which is the difference of original band gap, subtract this bias, will be smaller than electron hole binding energy. So in that case, electron hole can emerge as an exciton. So that's the idea. And in this case, because now imagine if I increase my bias, then I have more and more exciton form. But at the same time, the exciton binding energy goes down because of screening. So at some point, I will reach the condition that exciton binding energy goes to 0, and then exciton dissociate. So this bias voltage is the chemical potential of exciton. So I have a knob that can control chemical potential, control the population. Okay, so in this talk, I'm going to tell you how we experimentally realize this simple scheme and show you thermodynamic evidence for excitonic insulator, and show you a little bit of a recent result on exciton transport. And if I have time, I'll talk a little bit about putting those excitons on lattice. The building block is a monolayer of transition metal dialcogenide semiconductors. We've already heard from Mohammed yesterday. So you can just think of this as gap graphene. So the gap occurs at K and K prime points. This is on the order of 1 to 2 electron volts. And we have spin outer plane as Z as good quantum number, but spin and value are locked, so it has a time reversal symmetry. So we have double degeneracy, not full-time degeneracy like in graphing. And very importantly for this study, electron-hole binding energy is very big. It's on the order of a half electron volts. And that's order of magnitude larger than, for example, gallium arsenide and other conventional semiconductors. Okay, so we identified a pair, and this is not just restricted to those two TMD semiconductors. You know, many pairs can work, but there's some experimental details how to put contacts, separate contacts on those two layers. And this is something that we have worked on for years. And to have just the electron contact or hole contact is already challenging enough for this semiconductor, but have both. When it worked, you know, I even didn't believe it would work. So let me put this way, and that's the creative design by those two members of my group. So I'm not going to bore you with all the experimental details. So let me just point out a few key features of this experimental design. So we have, you can see the channel, which is the region we are interested, sort of with two layers very close to each other. So this is on the order of nanometer. And you can tune the thickness by inserting more or less hexagonal or nitride layers. But on the edge, on the side of a contact, we have a much thicker layers. So this is on the order of 20 nanometer. Okay. And the reason is because it's very hard to come up with good metal to match the semiconductor. And fundamentally because those monolayers are very sensitive to doping. So if you put something, the band can even shift. So it's very hard to find anything to work. So our strategy is to contact the channel, which is low density, to a contact region, which has a high density. And those two gate voltages, one of them will, this delta, will give us vertical electrical field. And that vertical electrical field will put those two layers at different potential. And right here, because the separation is big, so you can shift the bands quite a lot, so you can heavily dope this. But in the middle, you don't shift the band too much, but you still reduce the band gap somewhat here. Okay.
Gee, what's the horizontal size of this thing?
Okay, so this we can do on the order of a few to 10 micron. Yeah. So using this scheme, we can separate contact, you know, electron layer and a hole layer, and the electron hole injected from same device edge. So you can think of those electrodes as exciton reservoirs. They come from the electrons. Okay, so now let me just tell you a little bit about the thermodynamic measurement. And this is nothing but capacitance measurement, as we learned from the intro physics. So first, we would like to show that, you know, in that state, it's a charge insulating state, right? And then we need to show that in that state we can inject exciton. So to measure charge compressibility, we apply a small DC voltage on one of the gates and collect the charge on the other gates. So here is an example, you know, for certain outer plane electrical field. We see 0 at some gate voltage, and then goes to large value, and then goes down. So when the whole thing, you know, when the Fermi level is inside the gap, AC electric field can penetrate through, and you get a large capacitance. And that's what this is. So those two edges are the electron hole band edge. So you can either read the gap from the separation between the two, or just integrate. You get a value for the gap size. And so if you apply a bias, now those two are split, and then what the gate voltage does is to shift those two together up and down, right? So at some point I can dope, the electron layer. At some point I can dope the hole layer, and then you can see the whole thing is smaller because now the effective gap size is smaller. You see this edge does not shift, and that's because we ground this edge. So this separation is the effective charge gap. So that's how we measure whether the state is charge compressible or not. So very similarly, to see whether the state is exciton compressible or not, we look at the capacitance between just the electron layer and the hole layer. And when you vary the bias, that's like you're shifting the chemical potential, and you look at the displacement current, and that tells you about the density change of the exciton. So effectively, this capacitance is the compressibility of exciton. And again, if you cannot inject the exciton, this value is 0. If you can inject, it becomes positive. And the black curve is one example. So in this case, we have equal electron hole population. I'm increasing my bias, nothing, until I hit some threshold. Suddenly, exciton is injected. And then if I keep it increasing, then again, the peak goes away. It's like injecting electron hole, but they are dissociated. And I can integrate this black curve, get the density out. And using this method, we can inject the exciton, up to 10 to the 12 per centimeter square. So, okay, so let me show you the result. Just to orient you a little bit, I first show you a product simulation. So what this simulation does, for fixed outer plane electrical field, I'm varying the bias and also the gate voltage. And without taking electron hole binding into account, we can divide the phase space, into 4 different regions. For small bias, in the middle, both layers are insulating, and then if you shift the gate this way or that way, you dope one of the layers. And only if you increase the bias large enough, then you get electron and hole in the double layer. So this is a simulation without considering electron hole binding. So now let me show you the penetration capacitance, which measures charge compressibility. And the red means the whole double layer is charge insulating. And you see this red triangle showing up. And this is not too surprising. That's pretty much we did electrostatic simulation. But now what's surprising is that when we measured the exciton compressibility, and again, for large bias, we expect electron hole pair to come. So that's the red area. And for small bias, they cannot inject. Right? But the surprising part is that when you look at the thresholds, compare those two plots. So this red triangle means the 2 layers are charge insulating. And this dashed line means that's the threshold I can start populating exciton. Then you see that this is lower. So that means, I have exciton binding, and I can read from this plot, the binding energy is on the order of 25 millielectron volts. And this value can be varied by varying the thickness of the HVN between the two layers, we can change this from a few millielectron volts to about 200 millielectron volts by pulling those two layers further away from each other. Okay, so let me just recap this experimental result. So by varying those two parameters, two voltages, we identify this orange triangle. This is the regime for excitonic insulator. So we cannot put a charge into the system, but we can put exciton into the system. Okay. So next, I would like to tell you a little bit about how to do exciton transport in this system. And there's a related study from Berkeley, Fan Wang's group using optics to detect exciton transport.
How this triangle in which you have the excitonic insulator depends on the excitonic binding energy?
Okay. Yeah. Yeah, so if you increase the exciton binding energy, the region expands, becomes larger. This triangular region becomes bigger. The phase space becomes larger.
But eventually it will break down.
Yes. So what's happening is this is the threshold. You start to populate exciton, and then more and more exciton coming into the double layer. But at the same time, exciton binding energy is shrinking. And at this point, we have the maximum number of exciton, but at this point, the exciton binding energy already goes to zero. So that's the picture. Okay, so a schematic of this drag counterflow measurement is like the following. So if we apply a drive current in one layer and detect the drag current in the other layer. So if we have exciton, then if I drive electron in this layer, so automatically I should have a whole current, same amplitude, but in opposite direction, accompanying this current. So in this case, my drag current ratio should be 1. If the excitons are not bound, electron-hole pair are not bound, then they just don't care about each other. You get a little bit of frictional drag, and that should be something small. And at the zero temperature, this friction drag is expected to go to 0. So equivalent measurement is to do open circuit. So in this case, instead of measuring current, we can measure the voltage, right? So if I have bound electron-hole pair, although I try to drive in one layer, but because the other layer is open, then current cannot flow. So in this case, the resistance is infinity. And only if I break the electron-hole binding, then you can flow the current. Okay. So let's take a look at the data. So this is the triangle we already discussed, where we have the excitonic insulated phase. This is the drive current. So I apply a constant voltage and measure the current in one of the layer, and that's the electron layer. Red means we have current, blue means no current. So when we see the electron layer is doped, which is this region and this region, then you see current lining up. And here is a little bit of an imperfection due to the device. So this is all as expected. And the point is this drag current. So now you see that the hotspot is showing up only in the regime when we have excitonic insulator. So in this triangular regime. So next I would like to show you a line cut. So I'm going to cut through this line, and this is the line when hole equal to electron density. And the temperature is 1.6 Kelvin. So let me walk you through the curves here. So we have the black line, which is the drive current, And you can see the drive current turns on when the bias is large enough, and then it keeps going. And this is also some imperfection of the device. The red line is the drag current. It follows the drive current. And then at this point, at some critical field density, suddenly it drops. And if you look at the ratio, in this regime, which is the excitonic insulating regime, we have perfect drag. And above some density, the drag ratio just goes to 0. And just to be sure that the two layers do not talk electronically, we also measure the tunneling current, and this is the blue line, it's negligible. So based on this, we can conclude that the exciton transport dominates. Yes, please.
I think, as I understand, it's a two-dimensional system.
Yes.
For two-dimensional superfluids, I'm used to conductivity being 1 over omega, and this conductance is a property of 1D systems. So why do we see 1D quantization in a 2D system?
So I'm not saying I have superfluid yet. So this is not yet.
But why is it still quantized? It's a 2D system, right?
Quantized? No, nothing quantized.
It's the ratio between.
It's the ratio between the drag and the drive. So because I have equal electron hole density and they are bound, so if I drive electron current in one layer, I must have a whole current of the equal amplitude in the other direction.
It can be just classical.
Oh yeah. Yes. Yes.
But can we measure frequency dependence?
We can, but not very high frequency. So that everything to do with how good your contacts are. So I hope you agree with me that in this case, exciton transport dominates from this perfect ratio. And we can look at the temperature dependence of the ratio. Yes.
So the bias is the bias across the sample. It's not the bias of the gate bias, right? It's VB.
Yeah. So this VB is the bias across those two layers. So what this does is to change the population of exciton. And what happens here is that you reach large enough exciton density, they dissociate, and then it goes
But
away.
then the drive, the current drive, is
Yeah.
also something that you can control.
Yes. So we have enough contacts on each layer.
Very good. So as a function of this drive, do you see that there is a threshold behavior that above some current you don't get a drag? So what I was confused is that so the x-axis and the y-axis is the gate bias and the gate was not the previous control plane. So this is the x and y-axis are both the horizontal gates. The vertical.
Oh. No. Okay. So this vertical axis is the bias between the two electron and hole layers. So what this does is to change the population. This is the chemical potential of exciton. And this x-axis is the gate voltage. What it does is to shift electron hole chemical potential together up and down.
Very good. Now you have also the source drain that you can drive at any current you want.
Those are tiny,
Nice.
tiny compared to, it's a small perturbation to those.
But it's a free parameter. It's not a thing that you measure, right? It's
Oh yeah. So I apply certain DC voltage, AC voltage on top of, I have in-plane. That's the in-plane transport. Yeah. So I apply a small AC voltage between 2 points on my one layer, and this is the current I can measure.
I see. And my question was that if I change that, how these regions change as a function of that source drain?
Oh, okay. So we try to limit this AC bias on as small as possible, so that we don't perturb this. Yeah.
So just to clarify, so the tunnel current is the leakage current of VB, I understand. Looking for the blue curve that you showed.
Yes, yes, yeah. And that's actually overestimating, yeah. Okay, so let me move on. I have 10 minutes left. So, so we look at the drag ratio as function of temperature. So first thing I want to point out, for relatively small density, if you look at the color plot, even up to 20 Kelvin, we get nearly perfect drag. There are two different ways to ionize exciton. One is thermal dissociation, and the other one is due to phase space overlap, right? So that's like very important at zero, at very low temperature. And we see this kind of a temperature dependence, to make a cut for a fixed density. And this can be very well described by Saha equation, which just describes the equilibrium between exciton and electron hole gas due to thermal dissociation. So then on the electron hole plasma side, the frictional drag is relatively small. I can also plot this in terms of drag resistance, open the circuit. And then for small density, that's when the electron hole are bound. You see this insulating behavior. When you lower temperature, it goes up. And that just tells me I have a bound electron hole. If one circuit is open, I cannot flow, even with the drive. But when I increase the density, they dissociate into electron hole gas, then it becomes metallic. And this resistance is due to friction. And if we zoom in, look at here more carefully, it goes T squared. It's a frictional drag. So I can analyze this whole thing more carefully and put everything in one curve. So on one hand, before reaching the threshold, the gap size decreases continuously. And on the other hand, I have the metallic behavior for high density. That's where I have electron hole gas. The AT square, that A coefficient shoots up by several orders of magnitude and looks like it's diverging. We look at the dependence, and it follows pretty well the cube dependence. But interestingly enough, that this cube dependence is not counted from zero density, but counted from this critical density. And that's something we still haven't been able to quite understand yet. But this shows that there could be some critical transition. So this could be a Mott transition, and that needs to be studied very carefully with higher quality sample. Okay, so one other thing we'd like to show is the density temperature phase diagram. Yes. 5 minutes. Oh, okay. So to orient you, I just put up first this proposed phase diagram for 2 layers separated by two layers of HBN. So density and temperature. So below this critical temperature density, we have exciton. Above, we have electron hole Fermi gas. And this is the degeneracy temperature, just estimated as density. We have degenerate exciton on both gas below this line, and above would be classical. And then you can have a BKT transition in 2D. So this is just proposed the phase diagram. From our measurements, we look at the interlayer compressibility, which is the exciton compressibility. This dashed line is the degeneracy temperature, just using the density. But by analyzing the compressibility, as a function of density and the temperature more carefully, our degeneracy temperature actually is not along this line. It's up, it's higher, okay? And what this tells us is that the interaction is very important. So the interaction, the correlation actually is 10 times even bigger than in helium. So that's kind of the phase space, And of course, it'd be interesting to go down to lower temperature, see what's happening. Okay, so I hope I showed you that we have thermodynamic measurement and also transform measurement to show that there's excitonic insulating phase. And we have done studies on doping the excitonic insulator. And this is a Bose-Fermi mixture. If you're interested, we can chat a little bit more about this. We don't have experimental evidence for superfluidity yet, but we have an idea how to pursue this. And I plan to tell you a little bit about the bosonic lattice model. Chairman, how should I proceed? Should go with question or just quickly fresh through?
Let's take questions.
If there are. Can you show the temperature density phase diagram for the drag again?
Oh,
For the one slide back, or the temperature versus density drag. Yeah. So what's the reasoning for why? I get the left side and the right side of the diagram, but there's a sliver in there where at zero temperature you got very little drag, and then as you increase the temperature, drag returns, and if you keep increasing it, it falls off again.
you mean this?
No, above.
Above here?
Yeah, so the red and the blue, no, in the top figure.
Oh, this. Okay.
Yeah,
So
there's a little overhang here where at zero temperature, it's blue is the drag ratio between 2.5 and 5. Then as you increase that
that's
temperature-
this. Well, okay, yeah. So so this drag has two contributions. One is due to exciton. The other one is due to electron hole, the free electron hole, and that's the combined result because somewhere near here you have dissociation of exciton, and they have different temperature dependence, so that's why you get something. Okay, yeah. So maybe I'll just tell you the idea. So I don't need to go into the motivation, but how to put a boson on the lattice. So Mohammed talked about pumping a little more to add in the Moray system. Well, anyway, so our idea to reach equilibrium exciton on lattice is to replace each single layer by a moray. So then in one layer you have electron-doped moray, and in the other layer you have hole-doped moray. But there's some technical challenges, So you have to make the two moray exactly the same lattice constant, and you also need to have a good lattice registry, of the two layers. And we have tried with some success, but those two problems I mentioned remain. So an easier version, I'll just show you the idea, then you can tell me to stop. Okay. An easier way to do is to do one moray, and the other layer is still free. Okay. But we make the distance much smaller than the moray lattice constant. That's our limit. So in this case, if I populate one charge per moray unit cell, in the limit of large U over T, this is going to be a Mott insulator. So U is much bigger than T. So now if I apply an outplane electrical field, I can move, align the bands, move some of the charge from the moray to the free layer. Right? But they are not really free they actually, because this distance is small, so they would like to sit on top of that empty spot. Otherwise, if you sit on top of this occupied spot, it's almost like you have double occupancy because this distance is very small, right? So if I move, for example, this guy over, then this guy will have to follow the empty spot. And that's the way you can think about the system. So if I do the transformation, this will just look like an exciton. And we in this paper, we show that this system, you cannot inject electron a hole, but you can continuously tune this electrical field to increase the density of exciton. So maybe I should stop.
We can take the one or two questions if they're ready.
Actually, no, I
First
can
one.
ask her later.
Let's take here first.
What is the dash? The transition is at the dash diagonal line between classical degenerate. Between classical excitons and degenerate excitons. There are 3 slides about this. Just before this one.
Maybe we can discuss.